In this video, I'll go over the shooting method algorithm for boundary value problems. After studying this video, you should be able to recognize a boundary value problem as opposed to an initial value problem, formulate a boundary value problem as an equivalent system of initial value problems, and implement the shooting method for a linear boundary value problem. We'll cover nonlinear boundary value problems in the next video. So recall higher order ordinary differential equations can be written as follows, where the nth derivative of y with respect to t is some function of ty, dy dt, second derivative, etc., up to the n minus 1 derivative of y with respect to t. And that nth order differential equation will require n conditions for a unique solution. So far, we've been looking at initial value problems, and for initial value problems, what we would know is the conditions of the solution function y and all of its derivatives up to the n minus 1 derivative, all at some initial value t equals t0. So we know everything at the initial value, and then we would just step the integration forward in time. Boundary value problems are formulated differently. It might be the same differential equation, but what's different is we know y at maybe two different time values, t0 and t1, or maybe we know y at t0 and dy dt at some t1. Also, boundary value problems are often expressed in space, so they'd be more a dy dx. Again, still a differential equation of a function and its derivatives. The one key difference here is that we don't know everything at that initial time t0. So let's look a little more at this difference. So on the left here we have a typical boundary value problem, second order. Both of these are second order differential equations. And on the left we have a typical boundary value problem in space. Second derivative of y with respect to x is some function of x, y, and the first derivative of y with respect to x. And our two boundary conditions are at x equals 0, we know the value y is equal to y naught, and at x equals L, we know the value y is equal to YL. So looking here at our solution, what we're saying is we would know right here that this is y naught and this is YL. And we need to find y of x to solve that boundary value problem. So in contrast, what we've been looking at so far in the class is initial value problems, again, usually expressed in terms of time. So the second derivative of y with respect to t is equal to some function of ty and dy dt. And the key difference here is that both of our conditions are given at t equals 0. We know y and we also know dy dt, the value of the slope, at t equals 0. And then we can just step forward in time. And here's a plot. We looked at this solution earlier in a previous video of the Van der Pol equation. And we have a plot of y in blue, dy dt in red, and we generate both of these knowing those initial conditions at t equals 0, and we can integrate them forward for as long of a time span as we want. So another key here is for an initial value problem we might have more of an open-ended time span of integration. For a boundary value problem we're looking at a fixed boundary between two start and end conditions. So why do we need a different strategy? Well, thinking about second order initial value problems, we took two basic approaches. We used Runge-Kutta methods or multi-step methods. In both cases, our approach was to write a second order differential equation as two first order differential equations, and then we knew y1 at t equals 0 and y2 would be the derivative, and it would also, and we would know that at t equals 0. And in both of those approaches, knowing those initial conditions at t equals t naught, we would just step forward in time using the ODE function f of ty. So we write those in that functional form, that standard form, and use our various approaches for an increment function or a multi-step method or a predictor corrector method to step the integration forward in time. And this is simply not the case for a boundary value problem. And that's because we don't know all of the conditions at our first point of integration. So there's two common approaches to boundary value problems. Again, the key thing making this a boundary value problem is that one of our conditions is given at some time or space x value other than 0. There's the shooting method, which we'll talk about in this video, and the finite difference method, which we will talk about in a future video. So let's talk about how the shooting method works. So the basic idea of the shooting method is actually we'll take that ODE, our second order ODE, and we'll write that again as a system of first order ODEs. So that's the first step. And we'll actually call this the equivalent initial value problem. So the issue here is we write this as a system of first order ODEs. Remember, what we know is y naught and yl are our two conditions. So when we write this as our equivalent initial value problem, here's our system of two first order ODEs. Exact same technique for doing that as we've done before. But one of these is unknown. So we don't know one of the initial conditions. We only know that final condition, yl. And the approach to the shooting method is actually, we're just going to guess that. We're going to guess the unknown initial condition and use an initial value problem solver. So for example, we might guess dy dt at t equals 0, run the solution, we'll run the integration, and we land at a different place, right? So this is not the target boundary condition. So this is why it's called the shooting method, because our guess, typically it's the slope that we're guessing here, is like we're aiming the solution at the target and then using an initial value problem solver, something like ODE45, using an initial value problem solver to integrate the solution forward and seeing if we hit our target. And so then the next step of the shooting method is coming up with an intelligent way to keep improving our guesses so that we can hit that target. We'll call that our target boundary condition. The shooting method algorithm is a combination of tools we already have, things we've used earlier in the class. So again, we'll start by converting the boundary value problem into an equivalent initial value problem, as I've just discussed. Then we'll guess the value for the undefined initial condition. So here's our solution again. Say we know y naught, and we might guess dy dt at t equals 0. Once we guess, we're going to use that initial value problem solver to integrate and solve for the solution and look at where we landed over here at the end of the integration where x equals L, and we want to satisfy this end boundary condition yl. So we'll continue to change our guesses, integrate to the solution again until our final solution, or the end value, y end, is equal to our second boundary condition. Call that BC2, or y at x equals L. If it's a linear differential equation, we can actually use a linear interpolation after we've done only 2 shots. So we can do 1 shot, then we can say do a second shot with a different guess here, and interpolate between our 2 shots for the correct guess. In other words, the guess that will get the aim, that will aim our shot just right so that we land at that target boundary condition. If it's a nonlinear differential equation, we can still do something better than random guessing. We can set this up as a roots problem. And we'll see the example of a linear differential equation here in the following example, nonlinear in the next video. So here's an example of the shooting method for a linear differential equation. The differential equation governing the deflection of a simply supported beam with a constant distributed load is as follows. EI, where we'll just call this quantity, EI is the flexural rigidity of the beam. That's Young's modulus times the moment of inertia of the cross section, if you've taken mechanics and materials. So that is a constant times the second derivative of y with respect to x is equal to WLx over 2 minus WX squared over 2, where W here is the magnitude of that distributed load. So the boundary conditions are y at 0 is equal to y at L are both equal to 0 because the beam is pinned to these supports at x equals 0 and x equals L. And what we want to do is determine y of x, given these values for the constants. So let's look at the MATLAB code to implement the shooting method to solve this problem. Here's our MATLAB code to implement the shooting method for this problem. So you'll see right here is our dy dx function. Again, just like we've been using for our initial value problems, we've written the differential equation as a system of 2 first order differential equations, and our dy dx function returns a column vector of y dy1 dx and dy2 dx. Our boundary conditions are in the next line, and then we have our guesses at the initial condition. So what we're guessing, we need 2 guesses, since this is a linear differential equation, 2 guesses for dy dx at x equals 0. So this is again like our aim, and we're going to aim our initial value problem solver, ODE 45, at that target boundary condition using these 2 guesses. So for our first integration, we call ODE 45 with the first guess. IC guess is 1. And then our known boundary condition, y naught. For this, and then all we save from that first guess, all we are interested in from that first integration is the last value of y1. Because we want to compare that last value of y1 to the target boundary condition, YL. So then we'll take a second shot, and the only difference for the second shot is that we're using the second guess. IC guess is 2. And then again we'll save the last value and put the shots together in a vector, column vector that's a prep for the linear interpolation. Then the next stop is the interpolation. And let's look for a second at how we're interpreting what we're doing here. So what we're saying is we have, if you imagine our shots, our y end values are on, we can imagine our yn values actually, the way we're going to interpret this is with our yn values on the x-axis and our initial condition guesses on the y-axis. And what we're saying is, well, our shot 1, call it here, if this was shot 1, got us to that guess, so this was with our guess 1, and then say over here, shot 2 resulted, we got to shot 2 from guess 2, and we can imagine a line connecting those two. And if our initial, if the value that we want, our target boundary condition, say is right here, YL, what we want to know is what's the guess to get YL. So we have our 3 points that we know for the interpolation are our target boundary conditions, our shots at the target boundary condition, and the actual target boundary condition YL, and the unknown value is our unknown guess. So for our call to the interp, our x value is actually the shots, our y value is our IC guesses, and our xx value, again using the same kind of generic variable names we used when we talked about interpolation, is the YL value. Then we're going to use the linear option, since this is a linear interpolation. And the last thing is this extrap option. That stands for extrapolate, and that's in case the YL is not between the two shots. And for a linear interpolation, extrapolation is okay because we don't have a function that has some curvature that might lead to a wildly inaccurate extrapolation. Since there's no curvature, it's okay if our shots do not bracket YL. So then the final step for the shooting method is to use that new initial condition here as so that's our successful guess for the target that hits the target, and we're going to use that guess for a final call to ODE 45 to get our solution. So our Y3 now, that's our solution that's actually worth something. And we can compare that to the analytical solution. So I've got the analytical solution here, and we'll just plot them to take a look. And you can see, looking at this plot, and you can download and run the code and look quantitatively at the plot, and you'll see it's very accurate compared to the analytical solution. Our shooting method solution is pretty much right on top of it. Those are the red circles in the graph. So as far as the error behavior for the shooting method, it's going to be the same as whichever initial value problem solver we are using. So in this case, ODE 45, what we saw before, is that's about 5th order accurate on a global basis, and even a little bit higher than 5th order accurate. Another note on computational cost, it's a little higher because we require 3 integrations for a single solution. So it does cost 3 times as much as a single initial value problem integration. And that's just something to be aware of. And we'll look at a nonlinear shooting method in the next video.